We have a space program. The dinosaurs didn't have a space program. So we've already made progress in terms of making sure we won't be taken by surprise by something of that magnitude. And we'd just like to finish the job, get down to the smallest and smallest sizes that would have any consequence, and make the Earth safer for everyone and safer for generations to come.
This is CBS Eye on the World. I'm John Batchelor. It is a great pleasure to welcome three men from MIT who are going to help me with a mystery, which is the mystery of the asteroid belt, the main asteroid belt. And every once in a while you read about the possibility of an asteroid plunging into Earth, as has happened many times before in the history of our planet. However, the question is, will we be hit by something we see coming, or will it come from out of nowhere? And by the way, how do we know where the asteroids are and where they're going to be? What tells us? How do we ascertain that data? There is right now underway the building of a new telescope in Chile, the Vera Rubin telescope, that will be mapping the whole sky constantly. And that is said to be a great boost for planetary defense. There is also a planned probe by NASA, NEO-Surveyor, that's going to look for near-Earth objects, something that could hit Earth. However, we have a new kid on the block, and these gentlemen are going to help me introduce how it is that they came to publish it in Nature magazine. That's the top-of-the-line, peer-reviewed magazine in Europe. The American side of it is called, the magazine is called Science, peer-reviewed. JWST, that's the James Webb Space Telescope, sighting of a decametre main belt asteroids in view on meteorite sources. There's the breakthrough. Professor Julien, I welcome you and ask you to help my audience understand what you're looking for when you're looking small, and why heretofore it was understood that it's very difficult to ascertain an asteroid under, say, 10 meters. Good evening to you, Professor.
Good evening, and thank you for having us. I think the first thing maybe to lay out is our capabilities until we publish these studies. So the main belt is this belt of asteroid that you can find beyond Mars. And until we decided to look at what we could do with the James Webb Space Telescope, we could use telescope mostly on the ground to find asteroids of 1 kilometer size in the main belt. And we were mostly detecting them by looking at how they reflect the light from the sun in what we call visible light, the same part of the spectrum that we can see with our own eyes. But the fact is that these objects, these asteroids that are all the way out in the main belt, are actually brighter in part of the spectrum that we call the infrared, things that you cannot really see with your own eye. If you look at a fire, as a fire is really hot, it looks white, and then as it's cooler, it gets redder, and at some point we can see that it's hot, but still it keeps on emitting. Those asteroids are obviously not as hot as fire, but they get to shine light in the infrared. And it happens to be that the James Webb Space Telescope is extremely sensitive in the infrared. This is actually what it's been designed for, to look at the edge of our own universe and study all galaxies and so forth. And so as it's looking throughout space, what we decided to do with Artem Burdanov, that's here, the lead author of the study, is to ask ourselves the question, when we looked at the universe, obviously the solar system is between us and the universe. What is happening in between us and what we're looking at? And what is happening is that sometimes there might be asteroids passing in front of what we're staring at. So we decided to look at how many asteroids were actually passing in front of us, appreciating the fact that JWST would be much more sensitive, meaning that it could detect much smaller asteroids. And what we find out is that instead of looking at asteroid down to 1 kilometer in size, we can find asteroid all the way down to 100 times smaller, so 10 meter in size, the size of a bus. And behold, what we were not expecting is that there were much more small asteroids crossing our field of view than expected, and that allowed us to reveal a whole new population of the main belt, a population that we say is driven by collision, meaning that after a certain size, asteroid can be ground up by collision, and that size is about 100 meters, we find out. So we revealed this part of the main belt population that is easily broken down to decametre size and even smaller. And those objects can progressively be moved away from the main belt and enter what we said to be the near-Earth object population. And that's the big change here.
Professor Binzel is a professor of planetary science at MIT. Professor, what is a near-Earth object? Why do we care so much about it? What is the risk here?
Well, as we know, most of the asteroids happily reside between Mars and Jupiter in the main asteroid belt. But sometimes Jupiter's gravity tugs on just the right way. Jupiter is the most massive planet in our solar system. It's like a big bully on the outer side of the main asteroid belt. And sometimes those tugs, gravitational tugs by that big bully of Jupiter, will change the orbits of a small asteroid. So it doesn't nicely orbit between Mars and Jupiter anymore, but that orbit becomes very elongated. And then that elongated orbit means that it can come closer and closer to the sun as it goes around the sun. And if the asteroid starts coming closer to the sun, it will cross the orbit of the Earth. And so if an object crosses the orbit of the Earth and can come near the Earth, we call it a near-Earth object.
And once it is a near-Earth object, we care a great deal about its path. And we discern that path on the basis of expectation or projection. There's in the news, and I congratulate you gentlemen for coming up with a news item to call attention to your success, about an asteroid small enough but large enough to be troublesome, and found in 2024, YR4. And there were initial calculations that said that it had this much of a percentage of chance of striking the Earth in 2032. How was that calculation done, and what is the scale, Professor Binzel?
Yes, so it's not unusual from time to time we find one of these near-Earth objects for which, when we see only a tiny, tiny slice of its orbit, we want to project that forward and try to see where it's going to be many decades into the future. And from time to time, we'll find one where we say, oh, it's going to come close to the Earth on some future date, but we don't have enough information to know exactly where it will be. And so that can give it a tiny probability of intersecting with the Earth. It just means we can't rule it out. So to try to deal with this in a way that makes it easy to characterize objects for which we have an initial uncertainty, we have something called the Torino scale, invented here at MIT. And it's a 0 to 10 scale, where 0 means it's a normal object that basically has no chance of ever intersecting with the Earth. At 1, it means it's an object that, it's kind of like the usual ones that pass by. And where we don't want to be is 8, 9, or 10, which means we know for certain it's going to be a collision with the Earth. And 10 would correspond to the bad day for the dinosaurs. So as we discover these objects, they tend to show up, or they're going to start showing up on the low levels of this communication scale, the Torino scale. And it's simply a way of putting them out there for people to see, for space enthusiasts to keep track. But as these become more and more common, I don't think they'll be particularly newsworthy.
And YR4 was initially understood to be a 2 or 3, which was unprecedented. What does that mean, a 2 or 3, and why did it get demoted?
Right. So initially, when we discovered this asteroid 2024 YR4, it crossed a threshold of having a more than 1% chance of hitting the Earth. That just simply meant that out of 100 simulations of where that asteroid could go, 1 out of 100 of the simulations would intersect with the Earth. And so, or in other words, the odds were 101 in our favor that it would miss. So this object crossed the threshold of 1%, which puts it in Torino scale category 3. One can go online and find these category descriptions, but probably one of the most important things about category 3 or category 2, or even category 4, which would be for a slightly larger object than YR4, these low categories emphasize that as we get more and more data, with almost certainty, we're going to be able to say, oh, never mind, this will go down to 0 probability, or at least Torino scale 0, which means less than 1 in 1,000 chance of intersecting with Earth. And at 1 in 1,000 or less, we say, that's zero, folks.
Asteroids, who become meteorites sometimes when they're small enough. We're looking for the one to whom it may concern, that would hit us in such a fashion that it would be discomforting to everybody underneath it, but also damaging to the earth. You all know the story of the dinosaurs who looked up one day and that was the end of the dinosaur as we understand it. However, Artem, Burdanov, Julien DeWitt, and Richard Binzel are here to help me understand what they've discovered. Artem, you co-led the study in Nature magazine using the James Webb Space Telescope to find small asteroids in the belts. How did you do it, Artem? Good evening to you.
Good evening. Thanks for having me and for your interest. It's a little bit even a funny story because we started searching for asteroids at our group at MIT as a side project because we have a lot of data that's focused on search for terrestrial planets outside our solar system. But from time to time, we see an object that passing in front of the stars that we study. We see that in the images, and those are the big rocks in our solar system. And we decided to, do a data mining and find them all in the data we already have. And then we applied this to we started applying this to the data from Hubble Space Telescope, and of course we thought about trying to do the same with the James Webb. And fortunately, James Webb Space Telescope has been observing a star called TRAPPIST-1 star, which harbors 7 terrestrial planets, and where some of them might be where some of them are in the habitable zone. So the Webb telescope was observing that star to investigate those exoplanets, and Julien is involved in those programs. And we noticed asteroids that were crossing the field of view of James Webb, and we decided, why don't we look further into that and try to find them all? And that's how it happened. So we found many more of them than we expected, and it is astonishing given how small the field of view of the James Webb telescope is. So all the majority of the ground-based telescopes or space probes that look specifically for asteroids, they image big portion of the sky. The field of view is huge, but James Webb is a very precise instrument with a very small field of view that dedicated to study individual objects. And it just happened to be that there are a lot of asteroids that happen to pass in the field of view of James Webb, which is very small. So that was surprising for us, but and unexpected.
Unexpected because there were so many? You didn't?
Yes, yes, and so small. Yes, so many and so small.
You've never seen these before. They're not supposed to be there. That's the surprise.
There are different models which predict how many objects of which size must be in the main belt, and of course there were models which said, yeah, there must be exactly this amount of objects with this size, but no one ever saw that, no one ever confirmed that before James Webb took a look and before we found those objects.
Julien, I come to you because at some point you were looking at TRAPPIST-1, which is of great fascination. It's an exoplanet with a system that may or may not provide detail about atmospheres, about evolution, period. And all of a sudden, you had this interference with all these asteroids. At that point, how did you explain to yourself that you were going to switch from TRAPPIST-1 to little bitty rocks? What made you do it?
Well, funny enough, the way we look at it is that we went from searching for life elsewhere to helping to protect life here on Earth. So we just double down on life there, life here, same thing. No, joke aside, that's how it happens. So we, as Artem said, we have this extraordinary system, the really the best system where we could search for signs of liquid water and life elsewhere, the TRAPPIST-1 system. And it's been the number one target in the context of exoplanetary science for the James Webb Space Telescope. So we knew that Webb was staring at that system for a long time. And that's why we decided to try to do this bonus science type of thing, using James Webb data for things that they were not intended for originally. And it panned out, which is why the news has been covering this as a new role for our best and most expensive telescope, Asteroid Hunter. And so the way it plays into planetary defense, because there's really two outcomes to our study. On the one hand, as we talked about, it reveals this new part of the main belt population, very small objects. So we talked about the fact that we knew of these kilometer-sized objects. There was like about 2 million of them that are known. And now we get a sense of how many small objects are there, and we're talking about billions, right? So that really gives us an order of magnitude. So most of these main belt is going to be dominated by these decametre objects. And why is our study relevant in the context of planetary defense effort? Simply because we show that we can keep on being sensitive, that we can keep on detecting or tracking objects of the size down to 10 meters all the way out to the main belt. And so why is that relevant? Because as we talked about before, our capacity to detect objects from the ground relies mostly on visible, so how they reflect the light back to Earth. And as soon as objects are a bit too far away from the Earth, we lose them. And so why we now know that 2024 year 4...
30 seconds, Professor. 30 seconds. Go ahead.
Yeah, sure. Now that we know that 2024 year 4 has a probability of 0% to impact the Earth, it's important to appreciate that we could have found ourselves in a situation where in April, we cannot keep on monitoring this telescope from the ground. What do? Do we wait until 2028? No. Now we know that we can use James Webb to keep on tracking it and refine the impact probability. So James Webb can be used from that point of view.
Richard, I come to you because of the Torino scale. It's a fascination. What is it that we're looking for, and what do we do about it if we find it? Something not necessarily dinosaur-sized, but bad enough to cause a lot of damage on the planet. What does that look like, and how do we know? Thank you, Richard.
Discovering an asteroid and figuring out where it's going to be in the future is a bit of a challenge. It's like trying to figure out what seat a fly ball is going to land off a home run hitter's bat right when you hear the crack of the bat. So initially, we just see a tiny fraction of that orbit, and we don't know where that asteroid is going to be in the future. It's just, you have to watch it for a long time. So sometimes as we're watching it, we can't be sure one way or another if it's going to hit or miss the Earth. It can have a probability that gets transposed into this 0 to 10 scale we call the Torino scale that was adopted internationally back in 1999. And if we ever get to the situation where we have an object which is category 8, which is a small object that might be a bad place to land on a small town, a medium size, a category 9 object is larger than 100 meters. And that kind of object would be regionally devastating. And more than a kilometer could be a threat globally, just in terms of how much dust and debris it would put up in the atmosphere. So out of the 0 to 10 scale, let's ever see 8, 9, or 10. The chances of ever seeing an object like that in our lifetimes is incredibly small, but it's not zero. So what do we do? What do we do if we found an object that was on a trajectory to intersect with the Earth? Well, fortunately, this has been thought about now in recent years with some level of seriousness among international agencies. There's an international group called the International Asteroid Warning Network that is composed of more than a dozen different countries and different agencies that look at the very specifics of any particular object that poses a hazard or could pose a hazard to the Earth. And they've done lots of tabletop exercises of different objects at different times, different amount of warning times, to try to come up with scenarios of what we would do. Most ideally, we want to find these objects long before, like decades before they would ever intersect with the Earth. Because the longer time we have, the more options we have. And among the best options is something we demonstrated with a mission called DART, the Double Asteroid Redirect Test. It was a NASA mission to smash into a small asteroid, harmless out in the asteroid belt, that we could then measure how that spacecraft smashing into it changed its orbit or deflected it a little bit. And that test was quite successful in showing a deflection of an asteroid orbit. And so if we have a long warning time, just a little bit of a nudge, many years, if not decades, ahead of when that asteroid would arrive to our vicinity, can knock it completely off course. And so that deflection with a lot of time is the best option we have for keeping the Earth safe from an unwelcome asteroid coming to visit.
When you say decades, do you mean more than 100 years, less than 100 years? Can we guess?
I would say decades, as in plural, 10 or 20 years. Once we discover an asteroid, when we get a good enough orbit on it, we can actually predict it more than a century into the future. And after that, all the nudges and perturbations by the other planets start to make those calculations difficult. So we, with enough time, and we observe a complete orbit, a typical orbit might be 4 years for one of these asteroids, like DUP 2024 YR4. It has a 4-year orbit, and it took us just a few months to pin down that entire 4-year orbit. We finally saw a big enough piece of it. And in fact, once we see 2024 YR4's orbit over the next 4 years or so, we'll know where it's going to be for centuries. And that's plenty of warning, of course, for considering all our options.
Artem, I come to you because what next for this discovery of the James Webb having a day job and a nighttime job and a job on the weekend? You report in your article in Nature that the James Webb is going to be observing 15 to 20 exoplanet host stars next. And of those 15 to 20, you discovered 138 by looking at the TRAPPIST, or you were looking at TRAPPIST and 138 showed up. Are there any projections of how many asteroids you're going to be able to find with 15 to 20 exoplanets?
So James Webb has already observed a lot and will hopefully observe a lot more. And among different observing programs, there will be this big program dedicated to the study of exoplanets. And those observations will be done in a similar way that the TRAPPIST-1 observations were done. So only in those programs we hope to find thousands of these small decametre asteroids, but potentially it's even more in all James Webb data, because James Webb observes, as you already mentioned, galaxies, stars, very different things from different scientists all over the world and the US. So our next step is to look at all that data that gathered and trying to find asteroids in all of that. And it will help us to map a 3D structure of the asteroid belt. And who knows what we'll find.
So there's data already available, and you're going to be archivists. You're going to plunge into the data that's already achieved. Is that correct?
Yes, that's correct. And we are waiting for the new data to come. So we'll be doing real-time processing as data comes in available, and we'll be looking for looking in the data that's already in the archive.
Julien, the Vera Rubin, I've seen many photographs of it under construction in Chile. And then there's the NEO Surveyor. What can they do that James Webb Telescope is doing now? Any different?
Yeah, that's a great question in terms of what's next for planetary defense efforts. So these facilities will help us sample or find, if you wish, all of these near-Earth objects that are quite easy to find when they get close to Earth, right? And so they can do this sensing, this census work for the near-Earth population, and the Rubin telescopes even more. What they won't be able to do in some instances for some of these near-Earth objects that are found as they are moving further and further away from Earth, what they won't be able to do because they either don't work in the mid-infrared for Rubin or for the near surveyor, they don't have the same size of a mirror, so the same aperture, they won't be able to be sensitive to objects as they move further away. And so in the instance where there is one of the objects, and we're going to find so many more in the near future, so I think it's important for the audience to be aware of the fact that as humanity gets better and better telescope, we're going to have more and more of these objects show up on the Torino scale. There might be at some point one of them for which we don't have enough time to observe and track its orbit, and we may not know where it will end up in the near future unless we turn to JWST and JWST keep on observing it when it's further and further away from Earth and help us get that impact probability. So that's how they would be playing team together. Most of the work will be done by Rubin, by Neo Surveyor, and then in some cases we'll turn to the JWST to get the final size of this object or the final trajectory if we cannot do that with the other telescopes.
So what we're going to learn is what's going to scare us? Is that what I just heard you say? The better we get, the more scary it's going to become?
I would look at it the other way around. We'll have more time to do all the things that Rick mentioned if we need to do them. So we're getting safer and safer by the day thanks to this technological development, both in sensing and then in intervening if we need to.
The Vera Rubin is the whole sky. Neo Surveyor probably is pieces of the sky. The James Webb is a very narrow piece. You put all three together, you get a good profile. Is that where you're going? You're going to put all three together?
I'll take that if I can do that. I think it's important to realize that the James Webb Space Telescope and Hubble Space Telescope are designed to study in detail very tiny specific directions in space. What's coming online with the Vera Rubin telescope and the NEO Surveyor telescope, these are all sky surveys. These are specialized telescopes, not to point in a really specific tiny part of the sky, but to see as much of the sky, in fact, the whole sky, and monitor the whole sky basically all at once. And so that's a very different kind of telescope, very different kind of survey. The Vera Rubin telescope and the NEO Surveyor telescope in space complement each other because for Vera Rubin, being a telescope on the Earth, it can only work at night. It can only look in the direction away from the sun in the nighttime sky. The NEO Surveyor telescope in space will have a capability of looking closer to the sun in a large region of the sky that we cannot see at any given time from the ground. And so they complement each other. The space-based telescope and the ground-based telescope complement each other in terms of giving us full sky coverage, kind of everything everywhere all the time.
Julien, you've got an unlimited budget. What do you want to do next about your discoveries, either in the main belt or TRAPPIST-1? Good evening.
Good evening. I think what comes next, you're giving me options here between asteroids and planet beyond the solar system. Considering everything we've talked about with regard to planetary defense and how we're doing great with upcoming telescopes, our capability to deflect asteroids, I think I would probably turn to exoplanetary science and then look at the next generation telescope in order for us to identify all of the Earth-sized planets that are close by, because so far detecting capabilities are only for the planet that happens to be passing in front of their star from our point of view. And that would require moving to techniques that we called direct imaging. And so direct imaging actually allows us to get sensitive to the light of planets themselves. And so there are different mission design in the pipeline. And so my preference at this stage would be to support truly innovative mission design, such as the Nautilus mission design that we can talk about at a later time, if you'd like.
Oh, yes. So we're talking about terrestrial planets, rocky, wet, in the habitable zone, near to Earth. How near? What is your range?
Quite further away than New York is from Boston.
Yeah.
We're talking about, say, within 100 light years. That's probably about the ballpark.
Wonderful. That is the future. Richard Binzel, what is your expectation for your unlimited budget?
The first thing I would do, and we're actually underway with the NEO Surveyor telescope, is to make sure we have adequate surveys to find asteroids, to find what's in our neighborhood. Let's do a complete inventory of objects, bigger than what came and arrived at Chelyabinsk back in 2013. Once we have a complete inventory of all those objects that are out there, then we can rest assured. It's sort of like insurance that we know we won't be taken by surprise. But along the way, as we're finding all these objects that come near the Earth, I like to think of asteroids not as foes, but as friends, because as we find these small asteroids that come near the Earth, some of them are very reachable, very accessible, with not a lot of rocket propulsion. In fact, less rocket propulsion than it takes to go to the surface of the moon and back. And so my next step would be that once we found them all, let's go explore, see which ones might have resources like water. And this could enable stepping stones for future astronauts to explore further and further in space. So I think of these near-Earth asteroids not so much as a hazard, but as stepping stones outward for human exploration of space.
Artem, your unlimited budget, and as with Julien, you can go deep exoplanets, you can go to the beginning, or you can stay in the main asteroid belt. What is your ambition?
So I think that I will use that money to build a network of ground-based telescopes that will be following up and studying in details all those fascinating objects that Vera, Rubin, and NEO Surveyor will find. It will be a lot of them, and we'll need a lot of telescopes to study them, to track them, to make sure they don't collide with Earth. Yeah, there are already a lot of telescopes on Earth used by many astronomers, but we will need way more telescopes because the object that will be found by NEO Surveyor in particular, they will be quite faint in the visible, and we would need bigger telescopes to follow them up from the ground to see them in the reflected light. So that would be my main investment.
Now, gentlemen, having spoken poorly and alarmed the audience, I wanted to remind everybody that an event like what happened in Mexico, Yucatan, 65 million years ago, is extremely rare and doesn't need to repeat. Is that correct, Professor Binzel? That could be a one-off, not a every 100,000-year event.
We think the event that led to the demise of the dinosaurs is something that happens maybe on timescales of 100 million years or so on average. And the good news is we've already discovered all of the largest asteroids out there that could possibly give us a repeat of the dinosaur demise. We have a space program. The dinosaurs didn't have a space program. So we've already made progress in terms of making sure we won't be taken by surprise by something of that magnitude. And we'd just like to finish the job, get down to the smallest and smallest sizes that would have any consequence, and make the Earth safer for everyone and safer for generations to come.
Would we have seen that one coming, the dinosaur killer? Is it big enough for us to have ascertained beforehand?
If the dinosaurs had a space program, they would have seen their nemesis coming easily, decades, maybe centuries into the future. And they were around long enough. They could have done it, but hopefully we're a little bit smarter.
Julien, they would have seen it. Would that mean that we can defend ourselves? I want to give people confidence that it's not going to take us out this afternoon.
Yeah, 100%. As we talk through during this hour, we both have the capability to sense, to detect these kind of objects, and we have the capability to do what needs to be done, as Rick mentioned, with the DART mission.
Wonderful, reassuring. MIT, 3 men from MIT on rocks, whether rocks in the asteroid belt or rocks on TRAPPIST-1. The article is in Nature magazine. I highly recommend it, and I thank Professor Julien DeWitt I thank Professor Richard Binzel. I thank Professor Burdanov, research scientist at MIT. This is CBS Eye on the World. I'm John Batchelor.